Hello students, so continuing our lectures on numerical analysis. In our last class, we studied Euler's method. So in this lecture, we will throw some light on another method called Runge-Kutta method. To solve the ordinary differential equation. This method is again based upon taking a step size, that is basically if you have a equation like this, dy by dx is equal to fxy, and with boundary condition 0, and you take the step size as equal to h, and you proceed by taking the first 5 terms of Taylor series. So you can see the first 5 terms of the Taylor series. If you expand, it actually forms like this. You have yi plus 1 is equal to yi plus xi plus h. H is, you can find the step size, plus 1 by 2 factorial, the first derivative of function f at xi by I into h square, and then the other terms. You take the first 5 terms and then you compare it with this expression, compare it with this expression, and like 1 by 6 k1 plus 2k2 plus 2k3 plus k4 to the power into h, and you get the values of the coefficients k1, k2, k3 and k4 as the following. This method was proposed by this method was searching for Runge, and we have another method given by Kutta that is a little different from this. Here the equation used is a little different. Instead of the previous one, they are using 1 by 8 into k1 plus 3 k2 plus 3k3 plus k4 into h, and the following coefficients are obtained. So we can use either Runge or Kutta to find out the solution of the differential equation. So let's take an example. Let's take an example. If this is the equation that we need to solve and we need to find the value of y3 using the step size as 1.5. So a step size of 1.5 means we need to perform two iterations. That means from 0 to 3, if the step size is 1.5, that means 0 to 1.5 will be I is equal to 0, the first iteration, and from 1.5 to 3, it will be I is equal to 1, the second iteration. So we are using the Runge's method. You can see that is 1 by 6 k1 plus 2k2 plus 2k3 plus k4 into h, and for the first iteration we have taken the values as x 0 is equal to 0, that is the origin, because we have been given this boundary condition, and we are starting with the step sizes once h is equal to 1.5. So now we have to find out the values of the coefficient. The first coefficient is this, and using the value also find the other coefficient. So you see k1 we obtained previously, so we have k2 here, k3 and k4. So if we put them into the Runge's formula, we come up with this value 4.365. This is the value of x1, right? But the value of y1, or the value of y at x1. So this was the first iteration. Now we move to the second iteration, where the value of x1 changes from 0 to 0.5, 0 to 1.5, because this step size has been added here. This becomes 1.5, and here it is. So the value of this is the second iteration, or I is equal to 1. So value of x1 is 1.5, and we start for the value of y1 is what we have obtained in the previous iteration, 4.365, and of course the step size is 1. So again, following the same procedures, finding out the coefficients, considering now x1 and y1 instead of x0 and y0 in the previous case, we actually find out this, and we come up with this value of y2 as this 2.759. So we ultimately come to the final of this solution. So the value of x2 is now x1, right? The value of x1 is 1.5. So if we add, our main objective is to find y3. So we need to go to x is equal to 3. So x2 is equal to x1 plus h. So initially it was 1.5. The initial x0 was 0. The next one was 1.5 with the first iteration and with the first step, and now x2 becomes 3 with the further addition of 1.5, and we obtain the value of the y2. That was our objective, and that came around 2.759. Now the exact value of y3 given is 2.763, so we can see that the error is very less, that is 0.1501. We find out by the exact value minus the obtained value divided the exact value into 100. So this is the answer. This is the error update. So it's very less. So this is how an equation is solved by the Runge's method.